Welcome everyone to the problem solving session number 12 of the course Mechanics of Material. This is going to be the last session. So today we will be seeing problems from stability, especially the buckling of columns. Let's start. Okay. So first, we'll see some problems from the topic of stability of structures, the basic concepts. So we saw in the lecture there are three possible states of equilibrium. One is say stable equilibrium, where if we displace the body by some location, it will come back to its original position. So we call this as stable equilibrium. And also we would have seen unstable equilibrium, where if we displace a body by a small displacement, it's going to change its position and entirely. That's unstable. And also there is another state where it is neutral equilibrium, where even if we give a displacement, the body is going to remain the same. Okay, so this is neutral equilibrium. Fine. So let's solve some problem of finding the critical load in case of rigid connected bars. Say suppose finding critical load. What do we mean by critical load? We'll see. Suppose if we have two rigid bars, A, B, A, say A, B, and another bar connected like this, BC, and here it is guided roller. Okay, fine. And there is a load applied here. The load is say P. Fine. And here there is a hinge support at C. The support is inch, and assume this length is say L by 2, L by 2, and there is a spring at the center, rotational spring with the constant spring constant say K. Okay. Now we need to find what is this critical load. What do you mean by critical load? For values of this P, for some values of P, this body is going to come back to its stable position. After a particular point, it goes from stable to unstable equilibrium. So that particular threshold value of the load we call as P critical. Right? So let's see how to solve. We just need to draw the equilibrium of the body. So let me draw the free body diagram of the body to find the equilibrium equation. So say this is actually, if it is straight, like if it is straight, the ABC is straight, there is no problems. So this is going to be remain straight, right? This is P, this is P, and this is A, B, and C. Okay. Suppose if you are slightly giving some displacement, uh, say we are rotating this, I'm going to draw a little magnified version, but assume this is slight displacement. Okay, now there is a problem, right? Until it remains straight, it's fine, but when it is slightly displaced, there is a potential, uh, it can go to unstable, right? So same P, and here also P load, and this is A, this is B, this is C, and here as usual spring is there, right? So this is that small delta theta, this is small delta theta. Now if this is delta theta, this spring has undergone a displacement which will be, this distance is L by 2, L by 2. So this will be L by 2 times delta theta, correct? Okay. Now, like if you want to write the moment equilibrium, we can write P times L by 2 into sine of delta theta. Here I assume sine of delta theta to be delta theta. This will be equal to K times, this spring would have undergone here one delta theta, here one delta theta, so 2 delta theta, right? Okay, if delta theta is small, we can write this sine delta theta as delta theta and we can just cancel this. So P critical would have been 4K by L. Okay, so this is how we find the critical load. Now, if P is less than P critical, it will be in stable equilibrium. Suppose if P is say greater than P critical, it goes to unstable, right? So this particular value, the threshold value, we call as the critical load. Okay, I hope you can able to understand how we wrote this equation. This is simply like external moment and internal moment induced, the moment equilibrium. The external moment is caused by the load P into force into distance. Distance is the perpendicular distance. This is sine L by 2 sine delta theta. Since delta theta is small, I am just writing L by 2 delta theta. And this spring, the moment induced in the spring is given by moment stiffness, rotational stiffness times the rotation, right? So this gives the induced moment. So external moment equal to internal induced moment. So from that we can able to get this. Okay. Suppose if we have, let's see some more case. Suppose if we have a bar like this, and there is some spring, and the other end is free. Now, like if we apply a load here, and if this is L, how it will be? Suppose if we are giving, this is the initial, so assume this is the final. So it goes here. Say this is delta theta again, some small delta theta. So this will be delta theta times L, right? And there will be a moment induced. What will be the direction of that moment? So this load will give us moment in this direction. So there will be opposite moment. So that will be K times delta theta. Okay, this is the internal induced moment. Now we can just equate as previous above, like P times L into delta theta is equal to K times delta theta. So P critical would have been K by L. Okay. Similarly, suppose if we have a linear spring, say suppose if this is say inch, and here there is a spring of linear spring stiffness K, and there is a load applied like this. Okay, now what will be the free body diagram? What will be the free body diagram? Say, assume this is my say initial. I should have drawn the initial in the dotted thing and final in the solid line. Yeah, this is better. Okay. Say suppose if this is initial, and say I am displacing it some distance. Okay. Say delta. Now this spring is here. This in the spring there will be a tension force induced, right? There will be a tension force, and because of this tension force there will be a force here. What will be the force? K times delta, right? K times delta. Okay, and there is an external force applied here, which is P. Okay, now I think we are ready for moment equilibrium. This is point say O. Moment at O is 0 because it's a hinge support. So this implies P times delta acting in this direction, and minus K delta times L. Say this is L, length is L, will be equal to 0. So this implies P equal to KL critical. Okay, fine. So this is how we find the critical load. So we just have seen what are the three modes of equilibrium: instability, stable equilibrium, unstable equilibrium, and neutral equilibrium. And also we have seen what do we mean by critical load and how to find it, right? So we just understood the initial configuration and the deformed configuration. So it's about the equilibrium in the deformed configuration. We don't take equilibrium in the initial configuration, right? So yeah, moving on, let's see some problems from Euler's formula. This was the first topic, and this is the second topic. So Euler's formula. Okay. Before going to problem, let me just write the formula, like how it came, and we'll go back. Right. So yeah. Say suppose if we have a beam. Actually, it's a beam column because there is no transverse loading. There is an axial loading here, right? And say this my coordinate axis is, this is x, this is y, and this is z. Okay. Now this beam will undergo a deflection like this. Since it bends, we can able to apply the bending formula, right? So this is minus sigma xx, the axial stress, by y minus y naught. This is bending along y axis, will be equal to mz moment by izz equal to e into d square delta y by dx square, right? This is for bending along y-axis. Similarly, we can write another equation which actually tells us the bending along z-axis. So this is sigma xx by z minus z naught equal to my by I yy equal to e into d square delta z by dx square. Okay, this is for z-axis bending. The two possible thing, we will see how which one governs the buckling, the y-axis or z-axis. It's going to depend on the moment of inertia value, the radius of gyration value. Okay, so with this, like if we cut a free body at a particular section, say like this, if you cut a free body, we are going to have some internal forces. Okay, this is external applied load. Internally, to satisfy equilibrium, there will be a P here, and this is say delta y. This is say delta y, and there will be a moment induced. This is the P into delta y is anti-clockwise, right? So it goes like this. So to resist that, we will have some moment in the clockwise direction. So that is mz moment. Okay, mz, which is p into delta y. And here the value of delta y assumes this is magnitude, because since our sign convention is above y is positive, so it's below, so it will be minus delta y in reality. So mz will be minus p into delta y. This we can write as eizz into d square delta y by dx square. Now this gives rise to a differential equation, d square delta y by dx square plus p by ei cz delta y equal to 0. Now this differential equation, when we solve, we will get a complementary function in terms of sine and cosine, and when we substitute the boundary condition, since it is simply supported at x equal to 0, y is 0, and x equal to L, y is 0. When we substitute, we can solve for the two constant. So I'm going to write the final expression that we will get. So you can watch the lecture, a weekly lecture for the detailed derivation. So this P critical is going to be pi square ei by L square. It's the minimum value, right? So there are other modes possible. So we are interested in the least minimum mode, because this is going to govern the failure. Okay, and this this is IZZ. Okay, similarly IYY also can come, but we have to be cautious in using which eye it is. If it's a circular or a square, no problems. But if it's a rectangle or if some other unsymmetric section, we need to take the I value which is along the minimum value. Okay. Now we can write the stress value also, critical compressive stress. This we say critical load. We say Euler's critical load. Okay, this is Euler's formula. So this load we call Euler's load or Euler's critical load, and similarly critical stress. Okay, simply divide this by area. So PCR area will give us pi square E. ICC I can write A into RZ square. R is the radius of gyration by L. A and A will get cancelled. So we'll end up in pi square E by L by R, the whole square. So this is sigma CR. Okay, this we say critical compressive stress. Right now, maybe I can ask a question. Suppose if my sigma CR is less than sigma Y, mm, what type of column it is? Is it a long column or is it a short column? Okay, think. What do we mean by long column and short column? In a column, there are two possible modes of failure. Say, suppose if we have a column like this, and if there is some load applied. Okay, so far, before this week lecture, whatever we have seen is this can induce uniaxial stress, and each of the material has something called yield stress. When the particular principal stress crosses the yield stress, so it's going to fail, right? It's going to fail. So that is what we have seen so far. But we just now saw the concept of stability, right? So because of this secondary deflection, the deflection induced the small deflection, right? So there is a possibility of stability failure, which we say buckling failure. Okay, buckling failure. So failure induced by buckling, and here it it won't wait till the material all the material gets yielded, right? So it will simply fail before that, way before that. Okay, so we have to be cautious. So that is sigma CR. That is the critical compressive stress that we have seen. Okay, this is buckling failure. Another failure is yielding failure. Yielding failure. Here, sigma Y governs. Okay. Now, the question which I asked you is, yeah, by the way, if a column fails by buckling, we call that as a long column. If a column fails by yielding, we call as a stout column or short column. Okay, long column and short column. Okay, it depends on what is the failure mode. Okay, we can map this to the slenderness ratio, which is this L by R. We say lambda. This is the slenderness ratio. Okay, in the design, we consider some critical value of this L by R. We say below that it is short column, and above that it is long column. And we mostly we prefer short column so that we avoid this stability induced failure of buckling. Okay. Now the question which I asked you is, suppose if sigma CR is less than sigma Y, so what type of column it is? Is it a long column or short column? It is, if sigma CR is less than sigma Y, which means my column can buckle before it yield. So it is a long column. Suppose if sigma CR is greater than sigma Y, we say it is a short column, right? Because before my column buckles, my column is going to fail by yielding, right? So yielding governs. Okay, of course, we can able to plot this expression, the sigma CR equal to pi square E by L by R square in a graph, and we can able to get this plot, nice plot. The Euler's curve we'll get. right? So this is sigma CR, and this is L by R, slenderness ratio. This is in general sigma. Okay. Now, say for steel, maybe if say E equal to 200 gigapascal, if we substitute 200 here, and say sigma Y is it's Fe 250, so 250 megapascal. When we substitute this, we will get a particular value, that is here it is 250, and for this 250 we will get a value around 89. So this is the limit. Okay, below this, if L by R, if L by R is less than this 89 for steel, we say it is short column, this region short column, and this region long column. Okay, this is without applying any factor of safety. Okay, directly there is no partial safety factor, anything, right? Okay, so this is the some of the concepts from based on Euler's formula. Now let's see some problem. Problem number one from this topic. Say this is problem number one. Say this is A, this is B, and this is C. Let's say problem number two for the day. So I'm given a simply supported column, the length of the column is 5 meters. It's made up of steel with Young's modulus 200 gigapascal, with an allowable uniaxial stress sigma allowable as 250 megapascal, is to support a compressive load of 50 kilonewtons. If a column has a circular cross section, the cross section is circular, find the radius of the cross section, radius equal to what? Required to safely support the load. Radius required to safely support the load. Okay, right. So this is what the question is. We have been given. Been given with some simply supported column made up of steel. Okay, there's some column, right? The length is 5 meters, and we need to find the radius. Radius equal to what? Right. So how to approach this problem? So we need to safely support the load. We know there are two possible modes of failure. One is buckling, another is yielding, and we have this allowable stress. So also let's see the critical compressive stress. Okay, so considering buckling failure, what is the critical load? Pi square EI by L square, right? For simply supported. So this implies 50 kilonewtons pi square to 200 gigapascal. I, let it be. I is actually for circle, it is pi d power 4 by 64 divided by L, which is 5 meters. So this implies D B 10 power 3, 10 power 3 cancel. 50 ones are 50 fours are 4 ones are 4 16s are. So D power 4 will be 16 times 5000 square divided by 5 cube. Let's use a calculator. 16 times 5000 square by 5. The whole power 1 by 4, so 0.25. Okay, so I'm getting around 59.9, 59.93 mm. So let's say 60 mm dia. So radius will be 30 mm. Right. So let's also check the yielding failure. Now, what is this sigma critical, which is this P by A? Okay, 5 P critical by A, so 50 into 10 power 3 by pi by 4 D square. So this will be D is there, okay, 200 into 1000 divided by 60 into 60 into pi. So it's only 17.68 megapascal, which is actually less than sigma allowable, right? So it's fine. So here the buckling is going to govern and hence it's safe. So the safe diameter or the radius required to support this particular load is 30 mm radius, okay, or 60 mm diameter. Fine. Let's take one more problem. One more problem from this particular topic. The problem, yeah, problem number 3. So the problem is a 2-meter long pin-ended column of square cross section is made of wood. So E is 13 gigapascal for wood and allowable stress is 12 megapascal. The factor of safety is 2.5, right? We have to find size of the cross section. Size of the cross section if the column is to safely support first subdivision 100 kilonewton load, second subdivision 200 kilonewton. Okay, so this is a question. I hope you'll be trying. So it's similar to the previous question, but only difference here we have factor of safety. So we have to be cautious in applying that, right, to the critical load. Yeah, let's start. Solution. Okay, you can maybe stop this video and solve by yourself. I urge you to do so that after you can match your answer with the answer which I am getting. So that okay, yeah. I hope you have done. Let's proceed. So first subdivision for 100 kilonewton. So for 100 kilonewton, what is the critical load, by the way? Critical load is actually 100, but factor of safety is 2.5. So we have to design for 2.5 times 100, which is 250 kilonewton. Okay. And what else? Yeah, length is 2 meters and E is also there. E is 13 gigapascal. Now we can write P critical as pi square E I by L square, simply supported. So this implies 250 into 10 power 3 equal to pi square into 13 into 10 power 3. Okay, I am writing in Newton mm square. That's why I am writing this as 10 power 3 megapascal, which is Newton per mm square. Okay, 10 power 3 into I divided by length is 2 meters, so I want mm, so I'll write 2000 square. Okay, so this when we solve, we don't know I. Uh, Square cross section. So yeah, we can substitute instead of I, we can substitute a power 4 by 12, right? For square, moment of inertia is a power 4 by 12. So the only unknown is the side length. So a power 4 will be 250 into 10 power 3 into 2000 square into 12 divided by pi square into 13 into 10 power 3. It's 10 power 3, 10 power 3 out. So remaining things, let's use calculator. 250 times 12 times 2000 square divided by 13 by pi square. The whole power 1 by 4. So I'm getting around 98.3 mm. Let's take it 100 mm. Okay, so A is 100 mm. Now, yeah, we can, of course, we can compare, we can check for the sigma critical, which is P critical by A. Okay, usually in case of sigma critical, we avoid the factor of safety. So the load is say 100 into 10 power 3 by 100 times 100. So which is 10. megapascal. Okay, so it is safe. Fine. See, factor of safety, we have to use with more intellect, because for critical load, we want to make sure that our column stands with more load, even though 100 is coming. Right, 100 is coming. If I am using factor of safety of 2.5, I'll design it for 250 kilonewton. Okay, so even though 100 is the maximum, so I don't we don't know, right? Tomorrow anything can happen. There may be earthquake. It can be anything. We don't know. So that's why we use the factor of safety. And there are a lot of uncertainties involved in the materials, in the construction. So we will play safe. So that's why we use factor of safety. Here, when it comes to finding stresses, we want to check for the material yield stress. So there, if we are going to use factor of safety, it's like it's it's a negative thing for us. Okay, it's not safe. It's not recommended. So there we don't use. Okay. So here it's 10, but our allowable value is 12. So it is fine. Okay. And now for the second subdivision, subdivision B, for 200 kilonewton. Let's solve it again. So instead of 100, we have to substitute 200. So 200 means P critical will be 2.5 times 200, which is 500. So we have to solve it. A power 4 will be, I'm just writing directly, 500 into 10 power 3 into 2000 square into 12 by pi square into 13 into 10 power 3. 10 power 3, 10 power 3 out. Let's solve. 500 into 2000 square into 12 divided by 13 into pi square power 0.25. So we are getting A equal to 116.95 mm. Okay, now let's find the sigma. Sigma equal to P by A, which is 200 into 10 power 3 by 116.95 square. This squared times 200, 123, which is 14.62 megapascal. Okay, so here it goes more than 12, which is allowable. So it's not safe. So this is not safe. Okay, we have to revise this dimension. So we'll find based on this allowable, sigma allowable is P by A. So A will be P by 12, which is 200 into 10 power 3 by 12. This implies A is nothing but A square. 200 into 3 by 12. So square root of this. I'm getting A equal to 129.1 mm. So let's say A equal to 130 around off. Okay, so the cross section recommended cross section is 130 mm by 130 mm. Okay, we have to be careful. Right, in this problem we saw the yielding was responsible rather than buckling. So we have to check both. Okay, it's not only one criteria. We have to make sure that it is less than the allowable limit. Okay, right. Yeah. So this completes the concept of Euler formula. I hope now you can able to solve problems on this topic. Now we'll move on to the next topic for the day. Same, but not with simply supported boundary conditions. What happens if I have other boundary conditions? Topic 3, other boundary conditions. Okay. Like if I have I'll write it directly. So other possible boundary conditions are I can have a fixed and free like cantilever. Okay. B and this length is L. Okay, so we can derive this, derive the values, the value of the critical load, and we'll find that mm, the only change would be in the effective length. Here, the effective length is 2L. Okay, this is LE, the distance between 2 points of inflection. So LE, this is 2L. Okay, so in the formula, what would happen? So here P critical will be pi square EI by 2L. Instead of L, we put 2L. So pi square EI by 4L square. Okay, this is one boundary condition, that is one end fixed and one end free. Second boundary condition would be both ends pinned. Okay, both ends fin. For example, like if I have column like this, it's also pinned, and here it's inch. Okay, so this is the case, and load is applied like this. Fine. Now this is what we have seen already. So here LE will be L directly. That so P critical will be pi square EI by L square. Third one, one end fixed and one end pinned. This end is pinned and sorry, fixed, and this end is pinned. Okay. Now here the effective length, like we can derive this, we will have a moment also coming into the mz from the fixed support. So when we solve finally, we will end up in this formula of Euler's critical load. P critical is pi square EI by 0.7 L the whole square. Okay. So the effective length is 0.7 L here. And finally, both ends fixed. So in case of both ends fixed, we will get the effective length to be half L equal to 0.5 L. Okay, so here the Euler critical load will become P critical equal to pi square EI by zero point 0.5, so zero point 0.5 L the whole square. Okay, these formulas like we need to know. Only thing LE matters. 0.7 L and here is 0.5 L. Okay, now let's see a problem based on this particular topic. Problem number 4. An aluminum column of length L. So there is column. Here it's fixed support. Okay, and in the top, there the support condition is different. This is fixed, say A and B. B is fixed, whereas at A, two smooth and rounded fixed plate restraint is there. Like let me draw. There is plate. Okay, here one and here one. Okay, and my load is P acting like this. Fine. And say my axis is this is y axis, this is z axis, this is x axis. Okay, so this aluminum column. So two smooth and rounded fixed plate restrain end A from moving in one of the vertical planes of symmetry of the column, but allow it to move in the other plane. So here we see this cannot move along this y direction because it's restrained, whereas it can move along this z direction. Okay, so in the x and z plane, in the x z plane, it is fixed, sorry, it is free, whereas in the xy plane, xz plane is this plane, this is x and this is z. In this plane, it is fixed, right? Because it cannot move, so we consider as fixed. So LE will be zero point 0.5 times L, whereas in the XY plane, XY plane is where this one, X and Y. Okay, in this plane, it is one side like bottom fixed as usual, but other side is free. Okay, so LE will be 2L. We have to be careful. So in the question, we have been given with a boundary condition such a way that in one plane of symmetry, it behaves as a particular boundary condition. In another plane of symmetry, it is behaving in another boundary condition. Now, this is a question. Now, what we have to find for this question is there are two things. First, we have to find what is the ratio of the dimension of the cross section corresponding to most efficient design against buckling. Most efficient design against for most efficient design against buckling. What is A by B? Okay, this is what we have to find. What, by the way, A and B are the dimension of cross section. Say this is B, this is A. Okay. And also we have to design the most efficient cross section. Once if we find the ratio, we have to design the most efficient cross section. Knowing that say L equal to 500 mm and E equal to 70 gigapascal aluminum, and say load is 22 kilonewton and factor of safety say 2.5. Okay, values are given. Okay, so let's start. So this is the question. So again I repeat, in a question we have been given with column aluminum column. The boundary condition is one side fixed, in another side there are two smooth and rounded fixed plate which actually restrains the other end from moving in one plane, but it allows to move in the other plane of symmetry. Okay, and now for this particular case we have to find what is the most efficient section ratio of the dimension against this buckling. Okay, and then we have to also design the cross section, which means we have to find the values of A and values of B. Okay, let's start. Again, pause the video and please try yourself, like would you be able to do. Maybe I can give you a hint for most efficient section, like what is the criteria, if I want the most efficient section. Just think, the hint can be in the slenderness ratio. slenderness ratio, right? For most efficient section, if for my section is most efficient, the slenderness ratio along this two axes, that y and z, it has to be equal. Okay, if suppose in one direction it is higher, in another direction it is lower, my column is going to fail early. Correct? Yes or no? Yes. So to make it most efficient, we have to equate the slenderness ratio in two different direction to be equal. The y and z direction to be equal. Okay, this is the hint. Now I think you can try. You can pause the video and please try by yourself and then continue with the video. Yeah. Hope you tried. Let's continue. So the slenderness ratio, maybe I'll write buckling in XY plane first. First is say XY plane. Just a minute. Yeah, yeah. So buckling in XY plane. Where is XY plane? This is X and this is Y. Oh, I have swapped it here. Sorry for the mistake. Here, see, this is the picture which I have drawn here. This is XY plane, right? So this is X, this is Y. Okay, so this particular plane in yellow. Okay, this particular plane. For this, if I want buckling, these two are will act as restraint. So this is not free. This is we'll say hinged, right, or pinned. Moment it cannot go, right? Translation is restrict, so pinned. So this will be zero point 0.7. Whereas in the other case, it is free, not fixed. Sorry, very sorry. Free. So it is 2L. Why it is free? XY plane is this. Maybe I'll draw with a different color here. XY plane is this, right? So here we see it is free, you know, in this here it's free, here it's free. So it can nicely buckle like this, freely. There is no restraint there. Okay, so that's why. So here it will be 2L. So this implies LE will be zero point 0.7 L. And what is IZ? Cross section A and B, Z and Y. So IZ is what? IZ is BAQ by 12. Okay. And RZ is IZ by A, which is BAQ by 12 by BA. So A square by 12. Now LE by R will be lambda for XY, LE by RZ, which is zero point 0.7 L by A square times 12. See, this R square equal to I by A, so which is I root of, so it will be root 12. Okay. Now, in the XZ plane, the XZ plane, what is L? LE is 2L. There we say IY, so ABQ by 12. RY will be IY by A. So this will be AB will go. So B square by 12 root of. Okay. This is B by root 12. RY. Now lambda will be lambda of XZ will be 2L by R. Now for most efficient design, for most efficient design, we equate this lambda xy equal to lambda xc. Okay, so this implies 0.7 L by A root 2 12 root 12 to 2L by B root 12. L get cancelled, root 12 get cancelled. A by B will be 0.35. Okay, this is what we have to find. Okay. Right. In the next subdivision, we were asked to design the most efficient section with the dimension given. So here the load is 22 with factor of safety 2.5. So the critical load will be 22 times 2.5. So it's subdivision B. Design. So P critical will be 22 times 2.5, 55. Right. Now sigma CR, we can equate sigma CR is what? Pi square E by LE by R square. Right. So also we can say PCR by A. PCR is 55 into 10 power 3 by A. A is it's a rectangle, so AB. Instead of A, I can write 0.35B. So into B. Okay. So this is equal to pi square into E is 70 gigapascal divided by LE by R. What is LE by R? We can write any one. L is given as 500 mm. So LE by say RY, when we substitute, we will get uh, 2L into root 12. Both are same, but 1000 into root 12. You get 3464. 3464 by B the whole square. Right? So that's it. Now, the only unknown here is B. 10 power 3, 10 power 3 cancel. So B square, B power 4, 55 into 3464 square divided by pi square into 70 into 0.35. Okay. So 55 into 3464 square divided by 70 into 0.35 into pi into pi whole power 0.25. So B is 40.65 mm around. Okay, therefore A will be 0.35 times B, which is 14.23. Okay, so that's it. So this completes this problem. Okay, the most efficient section. So here we would have learned how to consider the boundary conditions, and vary the effective length, and also we have seen for most efficient section we equate the slenderness ratio along the two axes of symmetry to be same. Okay, right. Fine. I think with this, we complete this boundary condition. So the final topic that we still have is the secant formula. The fourth topic, final topic of the day, secant formula. So, which is actually what will I do if suppose uh, the column has some eccentricity? Okay, so it's like same, say a simply supported beam here, and it has some eccentricity. So, because this actually models some realistic behavior, because so far what we have seen is only concentric columns where the load is acting exactly at the center, but in reality, there will be eccentricity, right? So it won't be at the center. So because of the eccentricity, there is some extra moment induced. So this is E. So that's what we are going to see. Okay, it's going to reflect something like this. And if you cut a section at a distance, say some distance, so if we take the free body of this, P and E is there, so there will be P, and this there will be a moment in the anti-clockwise. So to counter it, there will be a clockwise moment induced. Okay, this is the mz moment. This will be p times e plus this magnitude of delta y. Here it is, as per the coordinate system, it is minus. Okay. Now, same way, like we use bending formula, mg equal to I into xz into t square delta y by dx square. We equate this with eizz t square delta y by dx square is equal to pe minus delta y. So this gives rise to a differential equation d square delta y by dx square plus say p by I, we can write k square to solve the differential equation equal to k square e, where this k is nothing but square root of p by I cz. Okay, fine. Now we can solve this differential equation with the complementary function c1 cos kx plus c2 sin kx and the particular solution e. Right, so now if we apply a boundary condition delta y at x equal to 0, we get c1 to be minus e, and delta y at x equal to L equal to 0, we will get finally minus e tan KL by 2. Okay, I'm just writing the final result. So when we substitute everything, we will get the deflection expression, that is delta y of x is e times 1 minus cos kx minus tan KL by 2 sin kx. Okay, and if you want to find the maximum deflection, we can equate this d delta y by dx to be 0, and we will get at x will be equal to L by 2, maximum location. And when we substitute this value at the deflection, we will get e times 1 minus secant KL by 2. Okay, this is the formula we have to know for solving problem. Okay, for maximum deflection, right? And we also can find the stresses, maximum stress. So sigma xx actual stress will be, there will be bending stress due to the bending moment, and there will be axial stress due to the applied load, right? So this minus mz by izz y minus y naught minus both are this axial is compression, so minus p by a, and in bending expression we know we will have a negative sign already, right? So when we substitute the value of y and value of mz as pe, so and we can take p by a common, finally we will end up in e by r square. Okay, I can write a into r square, and this fiber location is yc max, maximum the extreme fiber, cos kx plus tan kl by 2 sin kx plus 1. Okay, right now at x equal to L by 2, we can get the maximum stress value. Sigma xx at L by 2 max will be P by A into E by R square by C max to same like previous simplification. This will become KL by 2 plus 1. Okay, this is the expression we need to remember. Okay, now yeah, we can again connect this with slenderness ratio and the stress P by A, and we can get some behaviors also, right? You can watch the lectures for detailed explanation of the same. That's right. Now let's see a problem based on this particular topic of secant formula. Problem number 5. Just a minute. Okay. So we have been given with the problem. It's similar to your assignment problem. The line of action of a 100 kilonewton load is parallel to geometric axis of a simply supported beam column with circular cross section of 150 mm dia and E equal to 200 gigapascal. And also we have been given with the length of the column as 8 meters. Now the load is acting not at the center, but the load is acting at a radial distance of 4 mm from CG of cross section. Now for this we need to find P critical, we need to find the deflection max magnitude, we need to find the location of maximum deflection, we need to find the bending moment maximum, and we need to find the compressive stress maximum. Okay, so this is the question. Let's start to solve. Solution. Now first, P critical is straightforward. So P critical is pi square EI by LE square. So pi square into what is E? 210 power 3. What is I? It's a circular cross section, 150 mm dia. So pi t power 4 by 64. So 150 power 4 by 64. 150 power 4 by 64 into pi. Sorry, 150 power 4 by 64 into pi. So 1, 2, 3, 4, 5, 6, 7. 2.4 485 into 10 to the power 7 mm power 4, right? Yeah. LE is 8 meters, so 8000. Simply supported, so LE is L. So this is actually gives us 200, 123 into pi divided by 8000 square. So 766.45 kilonewtons. Okay, so this is the first subdivision. Second, what is the maximum deflection? Delta y max, the magnitude of the maximum deflection is, we know, E into 1 minus secant KL by 2. K is P by EI, square root of. Right. P is 100 kilonewton, 100 into 10 power 3 by EI, 200 into I is 2.485 into 10 power 7 square root of, this will give this 10 power 3, 10 power 3 cancel, this will become 10 power 5, so 1 by 200 into 2.485 into 10 to the power 5. Square root of, so this K is 1.418 into 10 to the power minus 4. Okay, this is Newton per, E is Newton per meter square, so Newton meter square, so meter inverse, right? Here it is mm, no? So mm inverse. So this implies delta y max will be E is what? 4 mm. 4 into 1 minus secant of K is 1.418 into 10 to the power minus 4 L by 2. What is L? 8 meters, right? Yeah. 8000 mm by 2. So 1.418 into 10 to the power minus 4 into 4000 secant of this 1 point minus 1 I guess it is in degrees. 1.418 into 10 to the power minus 4 into 4000 secant of this, right, minus 1. So it is actually negative into 4. So actually this is minus 0.7427 mm. Since we are interested only in the magnitude, so I'll take 7427 mm. Okay. Right. This third question, location. Yeah, location we know this is L by 2. So it's straightforward. Location of maximum deflection by 2, which is 8 meters by 2, 4 meters. Okay. And D, bending moment max. Bending moment max. You know, mg is what? P into E minus y max. Now just substitute delta y as delta y max. So P is 100 10 power 3 into E is 4 in minus of, there is a minus sign, it will become plus 4. So be careful. Okay, this will be plus 4 into 1 2 3 2 3 4 5 4.743 to 10 power to 345 Newton mm. Okay, mg max. Finally, the maximum compressive stress. Okay, E. So sigma xx max equal to, the formula is P by A into EYC max by R square secant of KL by 2, right, plus 1. Now, what is YC max? It's extreme fiber location. So, if YC max is, it is circular, so it's D by 2, 150 by 2, 75 mm. This will be P is 100 into 10 power 3 divided by area of cross section pi by 4 into 150 square into E is 4 to 75 by R square. R is radius of gyration. I by A. R is how much? 2.485 into 10 power 7. 2.485 into 10 power 7 divided by area of cross section pi by 4 into 150 square, the square root of 2.485 into 10 to the power 7 divided by 0.7854 into 150 into 150. The square root of this is radius of gyration value, which is 37.5 mm. So 37.5 square secant of K is 1.418 into 10 power minus 4. I think this we have already, no? Secant of KL by 2. Oh, I did not note it down. 0.418 10 to the power minus 4 into 8000 by 2 plus 1. So this implies we'll go inside out 4000 into 1.418 into 10 to the power minus 4 secant of this. Okay, this times 150 300 divided by 37.5 square plus 1 just a minute, screen sharing got stopped. Yeah, plus 1. I think I didn't added 1. Oh, okay. Okay, let me write 1.418 into 10 to the power minus 4 into 4000 secant of this getting inverse value. Where is the normal trigonometric function? Oh, okay. I'm not getting it here. Let me restart. Okay. Right. So 1.418 into 10 to the power minus 4 into 4000 secant of this times 300 divided by 37.5 square. Square. Okay. Um, this plus 1 into, let me write, so this gives us 1.213. This times 10 to the power 5 times 4 divided by 150 into 150 into pi. So finally, we are getting 6.8686 megapascal. Okay, that's it. So this actually completes the problem. Fine. So we just need to have the formula and substitute it properly without any careless mistakes. I hope with this you can solve the assignment problem. Maybe let me see if we have one more problem. Yeah, yeah. Let's see the last problem. Problem number 6. I'll just try to write the question and tell you how to solve. Problem number 6. Mm, Given a uniform column, say AB, there is a column AB, and here there is a load P, and it is not acting as a center. From the center, geometric center, the eccentricity is E equal to 20 mm. Okay. The length of the column is given as 2.4 meters. And the cross section has a structural tubing. So its cross section is something like this. Okay. This is the cross section given. The total is a square cross section, so 100 mm and 100 mm. This is your center. Say this is X, and this is say Y. And we need to find allowable centric load, allowable centric load, and the corresponding normal stress, and corresponding normal stress as per Euler's formula. Okay, so this is straightforward. We can simply write. Um, we can simply write P critical as what? P critical as pi square EI by LE square E is there, I is given, say area, everything is given, 2212 mm² and I is 3.3 into 10 power 6 mm per 4, radius of gyration is 38 mm, and the extreme fiber YC max, so it is 50. Okay, this is cross section details given. Now LE is what? So looking at this, it is fixed here and free at the other end. So LE will be 2L. Okay, so we can simply substitute all the values and we can find the critical load. Okay, this is straightforward. The second part of the question, we are asked, assume that the allowable load found in the previous part is applied at a eccentric distance of 20 mm. So in subdivision B, they have given eccentricity as 20 mm from the geometric axis of the column. Determine the horizontal deflection of the top of the column and the maximum normal stress. So we need to find horizontal deflection at top of column equal to what, and we need to find the maximum normal stress equal to what. Okay, so these two things we need to find, right? So as usual, we can apply this uh, thing y we say delta y max equal to E into 1 minus secant of what is the formula, secant KL by 2 na, right? Okay, everything is there. We can substitute and get the maximum deflection. Also, we can straight away find the maximum normal stress. That is P by A to 1 plus EYC max by R square secant of KL by 2. Okay, so it's straight away substitution. Okay, fine. That's it. So I think with this we come to the end of the lecture and end of the whole series of problem solving session. And first, let me just quickly summarize this particular topic. Today we've seen mainly four problems from four concepts. So first is relating the stability of structure. So we saw how to find the critical load corresponding to stable equilibrium by using then we saw Euler's formula and how to find the critical load, Euler's critical load and the compressive stress. And we saw two modes of failure by buckling and failure by yielding. And we saw the importance of slenderness ratio in classifying long column and short column, and some problems for finding the applying the Euler's formula. And we saw we have to make sure that we check both the criteria, the buckling failure criteria as well as the yielding failure criteria. And what else we saw? Yeah, what happens if I change my support condition from simply supported to say fixed or fixed pinned, and only thing the effective length will change, the Euler's formula will change. And we saw a interesting problem where we had a different boundary condition in one plane of symmetry and totally different boundary condition in another plane of symmetry. So we have to be cautious, like while applying the formula, the effective length values, right? And also we saw how to design the most efficient section. And finally, we saw what happens if we have eccentricity in the column. When the column is not acting at the center, if it acts at some radial distance e away from the center of the cross section, we saw how to find the maximum deflections and the stresses and the bending moment, right? So with this, we come to the end, and yeah, I hope you had uh, the problem solving sessions, all the 12 top weeks. I hope it would have been useful, especially for solving your assignment problems, and also to learn the subject more by solving problems. And if you have any questions, you are feel free to ask in the discussion forum, and you can solve more such problems from the textbooks or anywhere, any other materials you find. So the more we solve problems, the more we are familiar with the concepts. So I thank you very much for listening to the lectures in the past few weeks. So I hope you had a great experience. Thank you very much. With this, I stop the lecture for problem solving session number 12, as well as the series of problem solving. It's a great privilege and pleasure from my side. It's a good experience for me as well. Thank you. Thank you very much. Bye.